Now let's take a look at and understand some redox reactions. All right, so when we look at our redox reactions, we've talked previously about different types of reactions. So when we look at redox reactions, there's several types of reactions that wind up being redox. Our combination or synthesis reactions do. Decomposition is going to be redox. Single replacement, that's where we used the activity series, if you recall. Okay, and then combustion is also going to involve change in oxidation number. So let's take a look at just a few of these reactions. All right, so here's a combination synthesis reaction. We have some potassium and some chlorine gas that ends up giving us some potassium chloride. So let's take a look and understand how this is redox. You can see that I have some numbers written up in each of these. Those are the oxidation numbers. Okay, so let's take a look at it again. So I've got this balanced equation, 2 potassium plus chlorine is going to give me 2 potassium chloride. So we had a 0 here, a 0 here, a -1, and a +1. Okay, so I mentioned that we have to have the charges balance. So when we do redox, we can actually split things into what is called a half reaction. I can have an oxidation half reaction, and I can have a reduction half reaction. And I can balance these with electrons to make sure that we understand the flow of electrons. Now in this case, potassium went from a 0 to a +1, so it got more positive, so it was oxidized. Chlorine went from a 0 to a -1. It got more negative, so it was reduced. So let's take a look here. So I have potassium going to potassium ion, okay? Now, when I balance off a redox reaction, at this stage, to make my charges balance, the only thing I have available to me are electrons, and electrons are negative. So I have to put electrons in a spot where it's going to balance the charge. So we have that 0 here and that +1 here. Okay? So if I add a negative charge to the reactant side, I'll have a -1, and then my product side will be a +1, and that doesn't work. So I'm going to put my electron on my product side here. Now I get a -1. So 0 +1 -1 gives me an overall of 0, and 0 equals 0. Okay, so for oxidations, for oxidations, electrons are products. Okay, now I can do the same thing for my chlorine. Okay, so I have my 0, and now I have that -1 there. So I have a 0 here. 2 times -1 gives me an overall -2. So again, the only thing I have left are electrons. So now I'm going to put in 2 electrons over on my reactant side. Now I get that -2, and so -2 equals -2. This is reduced. Now, we have to make sure that the electrons cancel. So I have 2 electrons for my chlorine, but only 1 electron if I look at the potassium. So what I would have to do is I'd have to multiply this whole thing by 2. Okay, so I'm going to put it down here. I'm going to get 2 potassium. I'm going to get 2 potassium ion, and I'm going to get 2 electrons. If I put it all together, my electrons cancel, and I'm going to get 2 potassium plus my chlorine gives me 2 potassium ion plus 2 chloride ion. And indeed, one thing that will happen is if we have an ionic substance, let's say I took that potassium chloride and dissolved it in water, it would disassociate into those ions. I have it as a solid, so I can recombine this, and I can have my 2 potassium plus my 2 chlorine gives me my 2 potassium chloride. And does that look like our original equation? It does. Okay, decomposition, also redox. You can see I've got those numbers above there. I've got my mercury 2 oxide, liquid mercury, its elemental state, and oxygen gas. So I can do the same thing. I can write out my reaction here. Okay, and so I had a -2 and a +2, a 0, and a 0. Okay, so my mercury went from +2 to 0, and my oxygen went from -2 to 0. Now let's say that you're looking at this and you're going, I just don't actually, I can't figure out which is oxidized and which is reduced. Well, you can do that balancing by half reaction thing. You can look at the half reactions and figure out where the electrons go. So let's try it with the mercury. So my mercury is that +2 ion there, and then we're going to get that liquid mercury here. Okay, we don't need that though when we're just looking at these. But just a reminder that mercury is liquid. 2 elements on the periodic table exist naturally as liquids at room temperature. That's mercury and bromine. So if I have a +2 and a 0 here, okay, what am I going to need to do to make sure that I balance off those charges? Well, I need to add electrons somewhere. I can't add them to my product side here because it'll just end up making a +2 equals a -2, and that doesn't equal each other. So I'm going to put 2 electrons over here. So let's see if this works out. So I'm going to get -2 + 2 and 0. +2 and -2 gives me 0, and 0 equals 0. So if my electrons are on the reactant side, okay, are we oxidized or reduced? Did we gain or lose? Well, we gained. So when electrons are on the reactant side, we're reduced. Okay, and now I can do the same thing for my oxygen. Add that oxide ion. Gives me my O2 gas. Okay, all right, so we end up with or 0 and our -2. Okay, and we are able then to figure out that, well, to get a -2 on the other side, I've got to put, there we go, 2 electrons there. So I'm going to get a -2, a 0, and a -2, which is an overall -2. Now, if I were to try to put this back together, my electrons would cancel out here. But if you notice, I have the coefficients in front of the mercury up there. That's because we also have to have the atoms balance out, and there's 2 oxygens. So what I would have to do is, well, whoops, I have 2 oxygens there, which means if I want all my charges to balance out here, 2 oxygens at a -2 is actually a -4. So I need 4 electrons. And now I can get a -4 equals a -4. And oh, that looks better. Now my atoms balance. So that's another thing. When you look at these, you also have to make sure that it's not just your charges that balance, but your atoms, because I had O2. And so I had to have 2 oxide ions down when I looked at this right here. Okay, and so then I could, multiply this whole thing by 2, and then I would get 4 electrons plus 2 mercury, 2 ions, gives me 2 mercuries. I put it all together, those cancel, and indeed I would get okay. All right, let's look at one more type. Single displacement. Again, this is where we use that activity series. Let me try rewriting this. My Apple Pencil is not picking up correctly. That's better. Okay, so this is where we use that activity series. Okay, so I have some silver nitrate and some solid copper. And then I end up with this copper 2 nitrate and my solid silver. So a reaction happened. If I look on the activity series, what I will see is that copper is higher up than silver. Copper is more active than silver, okay? Which is why this reaction goes. So you can go back to the earlier chapter where we looked at this because we've talked about our single displacement reactions. We did that earlier, so make sure you review that to understand what's going on here. Now, if you notice, the nitrate ion stays the nitrate ion. It doesn't do anything throughout this reaction. So let's take a look here. Okay, so our full reaction here. Let's try rewriting this. Yeah. My iPad and my Apple Pencil are being really touchy. Okay, that looks better. All right, that's much better. All right, so now we had a +1 here, a +5, a -2, a 0 because it's in its natural state, +2, +5, -2, and then 0. Okay, so now what's happening here is the only things that are changing oxidation number are the silver and the copper. Now, the silver nitrate, that's an ionic compound. The copper 2 nitrate, that's an ionic compound. So ionic compounds, aqueous, which means they've been dissolved into water. So they actually split up into their constituent ions. So I'm going to rewrite this equation in a slightly different way. I'm going to write what's called an ionic equation. In fact, I'm going to write what's called a total ionic equation. So I'm going to account for everything that's here. So my silver nitrate is composed of a silver ion and a nitrate ion. I have a coefficient of 2 out front of that silver nitrate, which means that I have 2 silver nitrates. So I'm going to have 2 silver ions and 2 nitrate ions. Okay, my copper is just its solid copper. Okay, now I have my copper 2 nitrate. So that's a copper 2 ion. It's aqueous, so we've got our copper 2 ion. Now you notice there that I have that parenthesis and then that subscript of 2 outside the nitrate. That means that I have 2 of those nitrate ions for every copper 2 nitrate that's there. So I'm going to have 2 nitrate ions. Okay, and then I've got my 2 silver. So what's the same on both sides of this equation? The nitrate ion. So the nitrate didn't do anything. The nitrate is what we call a spectator ion. It did absolutely nothing. It started off as an ion floating around in solution. It ended as an ion floating around in solution. It did nothing. So now I'm going to rewrite this into what we call a net ionic equation. I'm only going to look at what actually reacted. Okay, so we get that. And from here is where we can split these up into our half reactions. I'm just going to go ahead and leave the coefficients on silver because I'm starting to run out of room on my slide. And then copper. Okay, and so when I look at this, silver's a +1, this one's a 0. So 2 times +1, I have an overall +2. And I have 0 there. So in order to get my charges to balance, I'm going to have to put 2 negative charges over here. So that gives me an overall 0. 0 equals 0. Copper, I have 0 here. I have +2 here. To get it to balance off, I have to put 2 negative charges here. So I'm going to get my 0, my +2, my -2, which will give me my 0, 0 equals 0. So we're good there. Okay, so this means that silver was reduced and copper was oxidized. And then if I cancel out my electrons, and voila, I get back what we had before. Okay, and again, this one is a single replacement, so don't forget that you need to be referencing an activity series when you look at these. If you're ever given two reactants that are doing a single, potentially doing a single replacement reaction, you have to look at the activity series and figure out which one's more active, which one's less active, and whichever one is more active wants to be an ion more. So if the more active element is already an ion, nothing's going to happen, no reaction. But if the more active element is not an ion, it will replace the less active element and become an ion. So you have to watch out for that with the activity series. You can also build an activity series too. If you're shown reactions and like this plus this gives no reaction and this plus this gives a reaction, you can actually start to piece together an activity series based on looking at, well, if this didn't react, this is more active than that. And if this did react, that is more active than this. And you can build all that together. All right, so that is it for understanding just the basics behind redox reactions.